Today we're going to deal with, I call it a religion. It's got to do with this branch of mathematical physics known as string theory. And string theory has become the mainstream without anybody noticing, right? You go back 40 years to the 80s maybe. String theory had no chance whatsoever. Nobody really paid attention to it because it was just starting out and everybody was just saying, oh, that's just math. And we cannot go to the lab and prove any of that. And so they didn't pay attention to string theory. But what has happened in the last 40 years is that quantum mechanics has made no inroads whatsoever. Okay? There's been no new theories. Everything is just as Niels Bohr and Werner Heisenberg left it 100 years ago. Nothing has changed. We still have Schrodinger's equation. We have Heisenberg's principle, etc. I mean, nothing has changed. There's no real new equation in quantum mechanics. All they've been doing, if anything, is creating this particle zoo, creating more particles, naming new particles that they think are coming out of their experiments. They see a trace here, another trace there. They call that one Charlie, the other one Johnny, and they just keep naming these traces. And that's the standard model in a nutshell. So there's been no progress in quantum mechanics. And so a lot of people got bored. And people who provide the funds, they say, well, just maybe the future is into string theory. Because string theory is an attempt to put quantum mechanics together with general relativity and unite, especially on the issue of gravity, unite these two so far irreconcilable tendencies, right? Okay, so where do we start? Well, we're going to start where we more or less left off last week. Here we have good old Galileo, and he said the following, which is pertinent to what we're going to be talking about today. Mathematics is the language in which God has written the universe, without whose help it is impossible, right, to comprehend a single word of it. Okay, that's what Galileo wrote. Okay, and he continues, says, I think that in the discussion of natural problems, we ought to begin not with the scriptures, right, but with experiments and demonstrations. So this was an age when this 17th century scientific revolution, so-called scientific revolution, started. Okay, and we haven't stopped in 400 years. Everybody today thinks, well, the Greeks were not making any inroads. They weren't doing any experiments, and that's why they had a lot of misunderstandings or misconceptions. And since the 17th century, hey, we changed all that because now we have experiments and we have math, and we put them together, and they're all a bunch of ignorance because of that, because they put experiments together with math. And you might say, well, what's wrong with that? I mean, what's wrong with experiments? What's wrong with math? Well, here you have an experiment for gravity, right? I let go of the pen and it falls to the floor, right? We all know that. Everything falls to the floor, unless there's some other force affecting the experiment, right? So we know things fall to the floor, but no one can tell me what's causing this. And you can't find out by running more experiments with a pen. I mean, how many more do you want to run? And you cannot tell me why the cause, behind this, the mechanism, by doing math. What equation is going to tell me, what's bringing it down? And for that, there's only one way, and that is, you have to identify, speculate, hypothesize, make assumptions about the invisible, intangible entities, physical objects, things that are in contact with a pen and which are either pulling it down or pushing it from above. That's it. You need to discover that before you do any math. And these people went out there and did a lot of math, and we still don't have the mediators, the invisible mediators that Mother Nature uses. And of course, like I say constantly, if you don't put a mediator there between the pen and the earth, you're doing black magic or witchcraft, voodoo science, voodoo physics. And in mathematical physics that's known as action at a distance or entanglement or something like that, you know. Anyways, so experiments aren't going to tell us anything anymore. We don't need any experiments to answer the type of questions we're asking, and neither is math. So neither math or experiments will tell us why, the explanations, the causes, okay? And he wasn't the only one, Galileo. Here he had this group of people, and they were among the most famous experimenters and mathematicians of the 17th century, okay? So it wasn't Galileo alone. And what do we put against this, against these people, against the scientific method of the 17th century, the one that started in the 17th century? Well, we have this. The language of physics is illustration. You have to illustrate, okay? If you don't illustrate, we cannot see your explanation, the mechanism that you propose, okay? That's the first issue. Then the other issue is that the mechanism underlying a phenomena is mediated by objects. You have to have an object, and there is no reason not to be able to illustrate an object, to point to one, okay? So you start by pointing, saying, this is a dog, this is a tree, this is a rock, and now you can do anything you want with it, because now the ET, you know, the Klingon who's visiting us from another planet, he knows our language. He knows what you're referring to when you say rock or tree, okay? And now you can do anything with that. You can explain a mechanism because you have objects to explain the mechanisms. They will serve as mediators, right? And then the other issue is no experiment will reveal the architecture of the invisible, intangible mediators that underlie phenomena such as gravity and electromagnetism. The only way to elucidate the nature of these secret agents is what? Through visualization. You must make an image or a series of images to show us how your mechanism works, how your theory works. What is a theory? It's an explanation, especially in physics, of a cause or mechanism. And no, neither math nor an experiment can tell you any of that about anything about a mechanism. Okay? So that's where we stand today. And why is this good as an introduction? Well, because string theory is just math. You know, it's criticized that it doesn't do any experiments. Okay, let's assume that that's the case. So we still have math. And the question is, you know, if math cannot tell us anything, you know, what's the point of having these mathematicians do research on math, on pure math? Okay, that's where it stands. And here it is, the definition we have from the Wikipedia, okay, for string theory, so we can put it in the right proper perspective here. String theory is what? A theoretical framework in which the point-like particles of particle physics are replaced by what? One-dimensional objects called strings. One-dimensional objects. What the hell could they be talking about? I mean, here, this is what they illustrate, okay? And whether you go with the one on the left or the one on the right, which is a string tied between two alleged brains, okay? P-brains, as I call them, P-brains of mathematics. You know, it looks like more than one dimension to me. It looks like at least two dimensions because I can see it. If it were one dimension, I wouldn't be able to see it. And when that thing moves, you know, up and down, is suggesting that it's moving into a third dimension because it's not moving along a plane, I guess. I mean, I'm assuming this, right? I've never seen a string that is three-dimensional so far, but maybe there is one out there. Right now, I see a two-dimensional, you know, rubber band that is moving in every direction, and you could say that, you know, if it moves forward or backward, we have three dimensions. There's no one-dimensional in front of our eyes. So whatever a string is, you know, this one-dimensional, I have no idea where they got this from, okay? And that's the first issue. The second issue here is you have another site that says the following. Let me get rid of this one. You have this site that says, please do not imagine that these strings are physical objects. So we're talking about one-dimensional objects, but they're not physical objects. Then what are they? What is a one-dimensional object? So we have a problem right off the bat because they need to tell us what they mean by a one-dimensional object. What is an object if not one that you can make an image of, and if you can't even make an image of it because what you're staring at is one-dimensional whatever, then we have absolutely nothing in front of us so far. So far, they failed already. It says they're not physical objects like the threads that you used for weaving or stitching. They are objects whose properties are similar to strings in the sense that their energy levels, whatever that is, right, are the same as those of vibrations of a conventional strings. Okay, so I again don't understand what they're talking about. They're saying that don't mistake these for sewing threads or strings. There's something else. You can't use them for stitching. They're not physical objects, but they call them physical objects. They use the word object to refer to them. And then they continue here. This is out of Quora, by the way, scientist, right? So just as we use words like spin to describe a quantum number, while elementary particles certainly do not spin like a top. Oh, that's the case. So they call it spin, but it's not spin. Great. Same way, the word string does not refer to thread-like structures. Okay, so all this bombs out all around. Okay, not only is the string not used for sewing, but on top of that, you have that this string is one-dimensional. They call it an object, and it's not an object. But here comes the best part. It says string theory describes. No, a theory does not describe. A theory is an explanation. If you're going to describe, you don't have a theory. Okay, you have a description, but not a theory. Maybe what is it? You can say you can predict with it. And prediction is just a description unless it's followed by an explanation, in which case you're talking about the past. You're pulling out of your experience to explain a prediction, the cause of what's going to happen in the future. And says, describes how these strings propagate through space and interact with each other. On distance scales larger than the string scale, a string looks just like, they're talking about what it looks like, and they're talking about 1D strings. And they say you have to look at it from very far away. Well, I mean, if you look at it from very close, up close, you got 1D, you can't see that. From far away, I'm not sure what you're going to see. You got to have, I don't know, Superman eyes to see that, maybe. It says a string looks just like an ordinary particle, whatever that is, because an ordinary particle, at least of quantum, is not a particle, it's a number. So a particle doesn't look like a little rock, a little stone, a little bead. A particle looks like a number, like number 5 followed by a unit. That's what a particle is in math. And so if a string looks like that, well, so far we have nothing. We just have a concept there. And it says, with its mass, charge, and other properties determined by the what? The vibrational state of the string. So they're going to talk about something in motion. They're talking about the vibrational state. And that's a contradiction right there, because state is a static concept, whereas vibrational is not. Vibrational is motion, dynamic concept, and state is a static concept. So vibrational state is already a contradiction, but it shows you what they have in their minds. What they say is that they're going to look at how this thing vibrates. They don't care about its looks, about, what it looks like, what the image is that you're going to put there for a string. And again, so in string theory, one of the many vibrational states of the string corresponds to the graviton, and a quantum mechanical particle that carries what? The gravitational force. It carries the gravitational force. How do you carry a force? You see, all the language is all screwed up in mathematical physics. They talk about carrying interactions, carrying forces, vibrating fields, which are concepts, moving a mass, and so on. The whole language is irrational. And it ends up saying string theory is a theory. And again, no, string theory is not a theory, because string is only math, and math is only description, and description is not a theory. So that's where string theory already dies. There's not much more to, as a prosecutor, I would rest my case. I wouldn't need to go further, because string theory already died right there. Okay, there's nothing to show. Okay, so where do we go from here? Well, Here we have examples of the string theory math. I'm going to give you two examples, right? So you can see what these guys are researching. What are they doing with their hieroglyphics? They're putting the little variables everywhere, you know. What are they doing? What are they doing with, what's all this money that's going into string theory? What is it used for? What's your money being used for? Okay, please ask that question to your congressman. Okay, what's my money being used for in string theory? And here it is. Okay, here you have just an example. This is just an example. It says one can write the following action for the string coordinates. Okay, so they're going to do a string coordinate. Okay, and it says whatever which encodes the area of the string worldsheet as a functional. So they're going to encode an area. That's what they're studying. They're saying, with this equation, you can encode an area. What does that have to do with how this universe works? I have no idea. And then in another part says the following. It says, its motion can be described. And again, they're talking about descriptions, and they're talking about theories. They're called string theory, and they're talking about describing an area, and they're talking about describing motion. I have no idea how they reconcile explanation theory with description. Okay, it says the solution for the string coordinates. In other words, they're going to just do math. It's just pure math. This stuff describes a position. Again, they're going to describe what we call location, but they call it position. What is a position? An ordered pair, an X, Y. It tells you how to get to the treasure chest, not where it is really standing, location with respect to other stuff in the universe. No, they're saying how to get there. That's what what position is in mathematics. Position is a dynamic concept, how to get there. Okay, and says and the velocity. Again, they're talking about velocity, speed, whatever, motion. Okay, they're going to quantify motion. Talk about the momentum, they talk about time coordinates, and again, all these are descriptions, dynamic descriptions, or descriptions of dynamic concepts, things that are moving. They're talking about how something moves, how much time it takes, and that sort of thing. What's all that got to do with, why does this pen fall to the floor? That's what I want to know. I want to understand that. What causes that to fall to the floor? That's what these people supposedly were researching all these years. And so we have one professor, at least, in Pennsylvania, and his name is Donald Semenek, and he says the following. He says, what sort of answers can science give? If you want some mystical, ultimate, or absolute answer, you won't get it from science. Philosophers of science point out that science doesn't answer why questions. Science only answers what? How questions. Science doesn't explain. Science describes. Okay? And so they're going to tell you is some description. And we kind of contrast against that math describes. So they're not talking about science. They're talking about math, which is quantitative descriptions. Physics is qualitative explanations. Whys. That's what a theory is. So we got a difference there, but the good professor here says, hey, that's what we do in mathematical physics. That's what we call science. We just describe, we don't explain. And that's so strange, because we have another fellow, and I want you to listen to him, okay? That way you hear it from the horse's mouth. Won't hear it from me. But here, this is what this fellow has to say, okay? Listen to him, and he's going to tell you something different than good old Donald Semenek, his member of the same club, right? So listen to this fellow, and he'll tell you what physics is all about. Okay, listen carefully.
What causes gravity? So physics, as you know, this is the type of question, what causes gravity? This is the type of question that keeps physicists up at night. Because physics is, among other things, as you know, the search for mechanisms, the reasons or explanations for why certain things happen the way they do.
Okay, so who's right? I mean, is physics about explanations, about physical interpretations, mechanisms, causes, whys? Or is physics just a description and we describe mathematically and get it over with, move on? So that's one of the issues. The issue is they have not defined what physics is about. despite 400 years since the scientific revolution, you know. So we have a problem. We have a problem because we have physicists here, so-called physicists and mathematical physicists, and they don't seem to be seeing eye to eye. But, you know, the funny part is that really James Beecham is correct. What you'll find is everybody out there, right? You go to Neil deGrasse Tyson, you'll go to, I don't know, Hassenfelder, Sabine Hassenfelder, Brian Greene. What do? They all try to do the same thing. They're going to try to explain a cause, a mechanism, and that's what they illustrate. They illustrate a mechanism, and then once you see it, say, okay, I understand that mechanism, but it turns out it's an irrational mechanism. And so when you point that out to them, they say, well, we don't do that anyways. That's philosophy, and we shove that onto the philosophers. And so, no, why are they doing stuff that is not part of their job description? They should stick to math and not be able to explain to the common folk what they're talking about unless the common folk take courses in math, advanced courses in math in college. But that's not what they do. They say, we're going to bring it to your level. And they bring this nonsense about warp number lines being gravity or particle being at two places at once. They bring all this nonsense. When you call their bluff, what do? They say, well, we don't do that anyways. That's philosophy. That's how it's handled, okay? So keep that in mind. Anyways, here it is, string theory. It's just pure math. Here you have a fellow who says it. Now, this is from the Wikipedia again. String theory has stimulated a number of major developments in pure math, okay? What is pure math? The study of mathematical concepts independently of any application outside of mathematics. Okay, so we have a problem because they're saying they're going to be doing pure math, and it doesn't involve anything outside of mathematics, but they say string theory is part of physics. So is string theory part of physics, or is it just pure math? You know, we have a contradiction there. I hope you see that. The appeal is attributed to the intellectual challenge and aesthetic beauty of working out the logical consequences of basic principles. So they're trying to establish some basic principles that apparently only apply to pure math. Okay, so we have the pure math there. It doesn't apply to anything outside of math, but string theory is part of physics. You explain that one to me. That went over my head. I'm sorry. I'm just not intelligent enough for that stuff. So yeah, this is my conclusion on that, okay? Math not equal physics, okay? If math is description and physics is explanation, you know, we don't need any math in physics, okay? So that's where we stop. And that, again, we murder math, string theory for the second time right there, okay? Because these people are just doing pure math that has nothing at all to do with physics, meaning with science. Math is just a language, okay? It's a language of hieroglyphics. That's all it is. And it's a language of relations, and it's a language of motion, of adverbs, quantitative adverbs. That's all mathematics has, quantitative adverbs. How something moves, you know, quantitatively. That's it. Okay, and here we have CERN. They tell us how these strings produce gravity. Hey, finally we reach what we needed to know. How does, that's what string theory was designed for, to explain gravity. They want to unite quantum mechanics with general relativity, have a unified theory, you know, the gut, the grand unified theory, or the toe, the theory of everything, right? And that's why they invented string theory. That's what it was all about. So here, CERN tells us how string theory produces gravity. Hey, let's hear from the horse's mouth again. This is out of CERN itself, okay? There it is. How does gravity emerge from string theory? And it says, force-carrying bosons of particle physics arise from open strings with endpoints attached to the four-dimensional subspace. Four-dimensional subspace. What is a four-dimensional whatever? Have you ever seen one? You know. And again, this is the problem. They're using language that has nothing to do with rationality. Okay? It's just an irrational language. Gravity arises from what? Closed strings propagating through space. Okay, so what was a string? Well, one of these vibrating little rubber bands. Okay, so it vibrates, right? And that's supposedly a particle, or the perimeter of a particle, I guess. I don't know. The point is it's vibrating, right? This rubber band. And it flies through space. Okay, so far so good. It flies through space. How does it produce attraction? I mean, here you have the pen again. Sorry, got to go with the pen. Pen, right? And all these strings are coming from the earth, or vice versa. Maybe go from the pen to the earth, right? And somehow these discrete entities flow back and forth or in one direction. I have no idea. And it produces attraction. How does it do it? What's the mechanism? How do you produce with discrete particles or discrete rubber bands? How do you produce attraction? And they say they flow through space. Okay, so they flow through space. I throw a rock at you. How do I attract you? Okay, that's the problem. It says, each fundamental force has its own corresponding boson. The strong force is carried by what? The gluon, right? There you have the gluon. It's that blue little ball there. The electromagnetic force is carried by the photon. That's that black ball there, okay? The weak force is carried by the W and Z bosons. That's that white ball there. And then, although not yet found, the graviton should be the corresponding force-carrying particle of gravity. This comes from CERN, okay, and it's that red one there at the bottom. So I guess that's what they're looking for in string theory. They're going to go to particles. I mean, if the particle is made out of a vibrating string, so what? How do you produce attraction by sending this discrete entity across space to the other object and then pulling on it? Please explain the mechanism. If anything, it would push it away, not bring it inwards. Okay, and again, like I say, the only force that mathematical physics has never been able to identify and never will be the force of pull. They can't produce pull, whether you're talking about entanglement, you're talking about gravity, whether you're talking about gluons trying to bring two quarks together. Any scenario, they don't have a mediator. And if they don't have a mediator, they have these little particles going back and forth that cannot produce the force of pull, the force of attraction. That's the whole problem. They have never had a force of pull because they never imagined that there are invisible, elongated, very thin entities that are connecting any two atoms out there in the universe, that connecting matter. That was the whole issue. And they never thought about it. And here you have, I've shown this before, this is Arvin Ash. He's a professor also, mathematical physicist, so-called physicist. And he's going to show you how to produce attraction with particles. And yeah, you got to see this because this is more or less what string theory is trying to do, even though he's not a string theorist. Okay, I want to caution there, word of caution. But he's going to do what string theory, what CERN just said. They're going to send this particle and they're going to try to produce attraction. So here it is. Let's go with the horse's mouth again. We're going to hear it from them. Listen carefully. Here it goes.
One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
Okay, so this is how they produce attraction. They have these peninsulas because they're not islands, right? They have this peninsula coming out, protruding out of the field. It's vibrating, that's why it's protruding. They call that a particle. It's not a particle, it's a peninsula, not an island. And somehow they come up with this other thingy that's out there who came out of nowhere, put in by hand, saying it's a particle, and that particle is the graviton is going to produce an attraction between two particles. That's their mechanism. Yeah, so the mechanism is really, waste of time listening to these people. None of them will be able to give you an explanation of how this universe works, especially gravity. And here's the punchline. This is from one of the professors at Stanford. And listen to him. Okay, here it is. He says, modern science is difficult and often counterintuitive. where intuition and common sense failed, they had to create new forms of intuition, mainly through the use of abstract mathematics. No kidding. So they started using abstract mathematics to try to interpret this world, right? When common sense fails, uncommon sense must be created. I like that. You got to be irrational. Then you're okay. Human cognition does not operate according to principles of common sense. So what we have here from this string theorist, he's one of the prime string theorists out there, is uncommon sense, known as irrationality. That's what they do, because they cannot explain their strings or even the nonsense of quantum mechanics. They cannot explain a single phenomena out there. All they do is do math, which are descriptions, and those descriptions do not amount to explanations. All the explanations of mathematical physics, especially quantum mechanics and general relativity, as well as string theory, are all irrational. All of them are irrational. Particle at two places at once, what sense does that make? You know, people just take it, oh, okay, the particle is at two places at once. How do they prove it? They say, well, if it weren't like that, computers wouldn't work. So they say that computers prove, right, because, you know, they did it with quantum math, computers prove that a particle can be at two places at once. And what they're really doing is saying that's their physical interpretation for what they think are particles, discrete particles. And then you have these fields, right? And from there you have these vibrations, which turn into these peninsulas, which are particles. And they throw these little discrete particles that came out of nowhere back and forth, and that produces attraction. So no, string theory has no chance of succeeding in science. But the important thing about string theory is something else. It's that it's displaced quantum mechanics, and at least in terms of funds, there are more funds going into string theory, and quantum people are very upset. They're saying, hey, you know, all these funds, we need to do experiments. We need to, you know, carry out with what the previous generation bequeathed to us. You know, we have CERN, we have SLAC, we have Fermilab, we have all these places. We need to do experiments and find out maybe how we can unite quantum mechanics with general relativity, you know, form the gut or the toe or one of those, you know. And all the funds are now going into pure math, into string theory. And what is pure math? Well, it's anything outside of it is not affected, meaning physics is not going to be affected by whatever money is pouring now into string theory. So that's a wrap for string theory. And that's for you to figure out. You got food for thought there, okay?